into the field. Her goal was to probe the temperature of the expanding corona. Since her first expedition in 1995, she has led 18 others across remote areas of the globe with her group, the Solar Wind Sherpas. These unique observations have unraveled some of the secrets of the corona and the expansion of the solar wind. So please welcome Dr. Shadia Habbal.
Thank you. Oh, just a minute. So can you see my screen? Somehow I'm not.
Was there for a moment.
Okay, let me try again. I just want to make sure. Okay, there we go. And I'll put it on full screen. Oh, I'm trying to get to the. Okay, sorry. Okay.
There we go. Looks great.
Okay, good evening, everyone, and thank you very much for attending this lecture. It's my pleasure to share with you some of the excitement, not only with the total solar eclipses, from the scientific point of view, which is really the reason that's driving me to do these observations, but also from a human point of view as to what, the experiences we encounter when we interact with people from different parts of the world, and also working as a team. How do we really have to be extremely well integrated so that everything works very well. So this cover picture is from the 2017 total solar eclipse that went over the northern part of the US. And my colleague Miloslav Dripmiller does the image processing. And you can see that there are incredible details in the picture. So the corona isn't just one homogeneous sphere of gas around the sun, but it has really what we call structures. So a few days ago, or almost a week ago, there was a total solar eclipse over the northwestern part of Australia. And I just got this video clip from Nelson Kwan yesterday, and I thought I will start with it just to give you an idea for those of you who have not seen an eclipse, how it happens. So you can see the excitement of the people, and so there was a very striking feature here.
Jupiter! Jupiter! Yes. Oh! Oh! 10, 9! Diamond Ring coming! Woo! Diamond Ring coming! There it is! Oh! Yes! Whoa! Cross is up now! Diamond Ring! Woo! Look now! Look now! Oh! Not fun now!
Okay, so for those people who have never seen a total solar eclipse, and even for those who have, it's always a very special moment when the sky turns really dark, and then you see this glorious apparition around the sun, which we call the solar corona. Now, this particular eclipse was very short. It was about 1 minute in extent over Australia. And what struck me when I was looking at it, and it's not very clear in this picture, is that around the whole sun, there was a rim that was very, very bright. It's not just what they call the diamond ring. And the reason being is that the angular extent of the moon relative to the sun was such that the blockage was exactly around at the rim of the sun. So there was a lot of what we call chromospheric emission, which is much brighter than the corona. But anyway, this was, all the people I saw afterwards who had never seen an eclipse, they said, I really understand why people go to the end of the world to observe a total solar eclipse. So I'd like to go back. a little bit in history, just to show you what people did before photography. So we have to recognize that people always saw the eclipse, but the only way to capture the eclipses, total solar eclipses, or the corona, was by sketching. So this is an example from 78, and you can see the very fine details that one can see with the eye. And these pinkish protrusions are similar to the one I just pointed out. They're called prominences. And they appear mostly pink because they're dominated by emission from hydrogen. The one on the right is a little more intriguing because what happened, there was this circular feature that was very rarely seen or recorded. And some people thought, well, maybe it's the imagination of the person who was looking at the eclipse. And I'll show later that this was one of the first records of what we now call a coronal mass ejection. So most of, and it is an underestimated fact or even unknown fact, that we really discovered a lot of what stars and their atmospheres are made of from total solar eclipse observations. So this spectrum was taken during the eclipse of 1869 over the US. And it's not the one I'm showing is a more modern one from our group, but it's the idea that you basically put like a prism and you can split the colors of what the colors that exist in the corona. So what was seen is that this green color that didn't correspond to any element that was known at the time from Earth or laboratories or whatnot. So they gave it the name coronium. And I must also mention that a yellow line was discovered around the same time, which was given the name helium. So helium was really first discovered in the spectrum of the solar corona. And this is important to keep in mind because all the knowledge we know about from other stars now really is based on what we know from the sun. So what were the consequences of this particular discovery? Well, it took, so that eclipse was in 1869, and it wasn't until 1941 that Adlin and Grotrian identified this emission as coming from the element iron that had lost 13 electrons. So for that to happen, the temperature, the iron has to be in a medium where the temperature is about 2 million degrees. So the implications of this major discovery was, one, that the corona, or what appears around the sun, is much hotter than the surface, which is at 6,000 degrees. Now, at that temperature, any gas cannot remain neutral, but it gets ionized. And some people, apparently the word electrified is more common, but I wasn't aware of it until one journalist told me that. But anyway, we, in the astronomical community, we talk about an ionized plasma, meaning that nothing exists without having lost electrons in their outer shells, any element. So Parker in 1958 came up with a theory that this gas that is so hot cannot remain bound to the sun, but has to expand, and he proved that it expands supersonically, and he called it the solar wind. Now, the solar wind so that was the theory, and it was also at the time where it was the beginning of space exploration. And in 1963, the existence of the solar wind was confirmed by a spacecraft, the Mariner 2, I think, or 3, that orbited, was close to Mercury, and they collected, I'll show you a plot. Another very important consequence of this discovery is that the corona then could be observed in X-rays, because at this temperature, you expect an object to emit in X-rays and in the ultraviolet and gamma rays. So it was also the beginning of space exploration to image objects in the sky in other wavelengths other than just the visible. So this was the Mariner 1 1963 detection. This on the vertical axis is the solar wind speed, and on the horizontal axis is the date. So it kind of wraps around. It starts from August and goes all the way to December. So this is from the paper. So what they discovered, so unfortunately, you have it's not so clear. I mean, the difference between the speed of the wind, the plot, and the density is very subtle. But what the darker one is the velocity, and you can see that it can vary anywhere from 300 to about 800 kilometers per second. And at the same time, whenever you have a very fast wind, you have a very tenuous, meaning the density is very, very low. And ever since this first discovery and confirmation, it has always been the case that this is how the two parameters, how many particles you have in the solar wind and how fast it's streaming, are opposite of each other. So when one is high, the other is low. So the big question was, okay, one, how does the wind produce these very high streams? The lower speed streams were more readily understandable from Parker's basic theory, but the faster one needed an additional acceleration mechanism. And this is what people in the field are still exploring. Now, of course, the other more fundamental question is, how does the corona get even to that temperature? What are the processes that are enabling this gas, which is above the surface, all of a sudden to get heated up to such high temperatures? Now, one thing that I also need to remind you, in case you didn't know, is that the sun and the stars are magnetic in the sense that in the convection zone below the surface, the interaction between the rotation of the star and the gas that's below the surface, this interaction causes magnetism to be produced, and it rises to the surface, and it's manifested in what we call sunspots, which sometimes disappear, and sometimes there are many of them. So this is this is a plot of the sunspot number starting from 1600 to 2010. And you can see that there is so if we just look at the blue curve, you can see that there's a periodicity, not with all the same magnitude, of the number of sunspots as a function of time. And this time frame is about 10 to 12 years. The sun goes through a minimum, meaning where you might not even see a sunspot, to a maximum where there is a large number of sunspots. So I won't go into the time when the sunspots disappeared, because that's not the focus of this talk. But the question then is, okay, you have these magnetic fields emerging from the surface of the sun. So do they have any manifestation in the corona? And sure enough, they do. These two images, one is taken, the left is from 2012, solar maximum, and the right is from 2019. So you can see how more complex the structures. So all these filamentary features in the corona are really magnetic fields, which become visible to us because all the charged particles have this property where they latch onto the magnetic field lines. And they also emit, but in the case of the electrons, which is this image here, so imagine you had plenty of electrons in the corona, which is the case, and each electron is spiraling around a magnetic field line. And as they're doing that, they're reflecting the sunlight from the surface of the sun towards in all directions, and we are one direction, which is the observer. So this is how you can actually trace the magnetic field lines in the corona. So you can see that the appearance of magnetism on the surface has consequences for the way the corona looks like. And you can see that from maximum to minimum, it looks very, very different. Now, I told you that with the discovery of the solar wind and the hot corona, then this was the beginning of space age. And now we have so many spacecraft looking at the sun in the X-rays and extreme ultraviolet. And you would say, well, why even bother with the total solar eclipses if you have all this rich repository of data? So I want to show you why we still do eclipse observations. This is an image from the Solar Dynamic Observatory, which observes the sun in different wavelengths. And you can see one of the advantages of the extreme ultraviolet is you can see the corona as projected onto the solar disk, as well as off the limb of the sun. So you see a little bit outside the sun. Now remember, during a total solar eclipse, the moon blocks the solar surface, so you won't be able to see this. And all you see is what's the corona as projected off the limb. Now, Leo was the first one in 1932. He was also getting a little antsy that the eclipses happen only every 12 to 14 months, 18 months. So it was a long time to wait for observations. Furthermore, they lasted only a few minutes if you were lucky. And if you had a cloud, well, you had to wait for the next eclipse. So he came up with an optical device, which is called a coronagraph. Basically, it's a man-made occulter. So you can block the solar disk and you can see the corona around it. But the disadvantage of the occulter is, this is one example from an occulter in space called LASCO C2. So the sun is occupying, this is the size of the solar disk. So these two pictures were taken at exactly the same time. And you see that there is this gap between the two where there is no information. So if you consider only the extreme ultraviolet and you look at the white light from LASCO, it is really difficult to imagine how the connectivity is formed, especially if you add the total solar eclipse image at the same time. So you would have never guessed that this is how the corona is close to the sun that connects the surface out to interplanetary space. And at the moment, with a natural eclipse, you can see very far from the sun. With a coronagraph, you can see only a little bit, because the sky brightness is not dimmed enough to be able to see the corona to larger distances. So this is one of the reasons we still do total solar eclipse observations, is to understand the connectivity between the sun and what expands into interplanetary space and actually shapes the environments of all the planets, including our own. So this one is another example to show you what you are missing in these coronagraph images when you look at the eclipse image. Furthermore, the beauty of eclipses is that we can keep up with the improvements in technological devices, in particular cameras or recording devices, to increase the spatial resolution of our images. Whereas when you launch something into space, it's there for 10, 20 years, and you can't really upgrade your equipment because it's up there in the sky. So this is the part which is really the impetus for doing total solar eclipse observations. And I would like to now share with you a little bit some of the science, what we do with the eclipses and what we observe, and why it's really valuable in addition to being exciting and fun. So it just so happens that if you recall in the first, I showed you a slitless spectrum, and I said Young and Harkness discovered this green line, which is actually this what we call now iron 14 line. So it's an iron that lost 13 electrons. However, the corona is far richer than that, and it emits in a sequence of iron lines going from iron 9 all the way to iron 15. So what does it mean? Is each one of these ions corresponds to a specific temperature. So for example, this is the ionization fraction, meaning how much iron 9 is there compared to the others as a function of temperature here. So you start with iron 9, and then if it's present, then you shouldn't really, or the emission from the other lines should be very low, meaning that each line likes to be formed at a certain temperature, and then it drops with the temperature. So for example, this iron 10 plus peaks around 1.3 million degrees. And you can see at this point, you could see emission from iron 10 in orange, or you could see a little bit of iron 9. If you go to the iron 14 line, which is 13 plus, you see emission at 1.9 million degrees. This is the purple one. but there is still remnant from the iron 13 line. So you have a mix, but you could get into situations where you really see only one of these lines. And then you say, I know that this gas that I'm seeing is at this temperature. And it just so happens that the corona is not at a unique temperature, but it's multi-thermal. So these are this is one example from the eclipse in Chile in 2019. And these are the systems that we have. So each wavelength we focus on has to be observed with a pair of cameras. And the reason being is the visible is like, imagine you have a mountain and you have some trees sticking out of the mountain. To just isolate the trees, you have to remove the mountain. And this is what we do. So one of the cameras is not centered on the emission line, but off by, like, say, 30 angstroms away. So it only captures this background mountain. The other one captures the mountain plus the tree. And what we do is we subtract the two from each other and we just get the emission line itself. So you can see that this is quite a complex system. And this is my colleague from the Czech Republic who put together 12 of them on one mount. So when we travel to eclipses, we hand carry all these optical systems, but we ship the mounts and the tripods. And here are some, of the laptops we were using. So every pair has one laptop. So these are expeditions from, I think the last one was in Antarctica in 2021. So you can see that they really cover an incredible part of the world. And this is fortunate and also really very enriching to us or anybody who goes to these places, because you can see how the fabric of humanity is the same throughout the world, and really the boundaries, geographic boundaries or man-made boundaries, really don't make sense. So this example is from 2019. So I showed you the instrumentation, and here I'm showing you the different images in these different emission lines. So each camera is tuned to a certain wavelength. So for example, this one was tuned to what we call iron 10. It's at 637 nanometers. It's at about 1 million degrees. And if you look at all four pictures, and if I didn't tell you it was the same eclipse, you might not have guessed because they look so different. So this right away, just looking at the images, you can see how different temperature gases exist in the corona. And if we just choose a certain temperature or a certain wavelength that selects this temperature, we see we can isolate it. So here we're isolating iron 10, whereas here you're isolating iron 14. And these two are almost double the temperature, but you can see how different the two images look like. Now we also can superimpose the two just to give a visual impression of how the two temperatures, or 3 or 4, whatever, are coexist in the corona. Now what we've done is, so in white light, this is what your eye sees. You actually are integrating over all these wavelengths, and you should see all the structures in the corona. But from white light alone, you can't really tell anything other than how dense the material is. But when you go to these what we call narrow bandpass filters, which we use with our equipment, then you can see what actually all this complexity here corresponds to iron 14 emission, meaning that in this region, the gas is really very hot. In the regions where, here in the polar regions, they're well isolated because it was solar minimum, they're very visible and evident. You can see that the temperature is a lot cooler. It's dominated by this 1 million degree corona. So at the moment, so far, we had collected close to almost 2 solar cycles of multi-wavelength observations, meaning we have about 15 years which straddle two solar cycles. So what could we get from this? They are more or less the same types of observations, except for the first one in 2006, where we observed iron 11 and 13. In the rest of the years, we observed iron 11 and 14. Now, The reason I just selected these two, because these are two of the strongest lines in the corona, and it just so happened from all our observations that these are really the dominant temperatures in the corona. So shown on the left are the white light images, and then next to them are these superposition of the iron 11 and iron 14. Now you see there's a huge gap between 2010 and 2015, and this was the unfortunate case of 2012 and 2013. We were clouded out, so we missed 2 times when the sun was at solar maximum. Now this year the sun was close to solar maximum, and fortunately we were lucky to get observations. So visually, when you look at these images, you can see that anything that's streaming away from the sun is dominated by iron 11 emission, the red emission here, which is around 1.2 million degrees, and everything that seems to be bound to the sun or forming some large-scale arches is at the much hotter temperature. So how do we try understand, or how is that this information, how does it get transported into interplanetary space with the solar wind? So this is just one image showing the coexistence of the two temperatures. And here on the right, I'm showing data taken from an in-situ spacecraft, meaning a spacecraft that's at one astronomical unit. And what it's doing is just measuring the speed of the wind, the composition of the wind, and the density, etc. It measures several things. But what I wanted to focus on is here, what we see in the corona is the dominant emission that of particles or ions that are streaming away from the sun are really produced by this iron 10 plus. This is dominant in the corona. So then we went to interplanetary space and we said, well, what kind of ionization states of iron is measured in interplanetary space? And what was really surprising is the ionization states vary as a function of time. And this we did for like 15 years, but I'm only showing you one example. And but the average, or the one preferred ionization state, is actually iron 10 plus. So this is the first direct link between what's observed in interplanetary space and originating from the sun, from different parts of the corona, where you can, it's almost like you have this one particle that you can trace all the way from the sun into interplanetary space. Now, the top panel here shows you the speed of the wind associated with the speed of the wind, the proton speed. And I colorized it just to distinguish between bands of speeds of 300 to 400, 400 to 500, and 500 to 700. So blue, red, and green. But you can see that no matter what the speed is, it varies significantly. The band here remains almost constant. So it means that the wind is originating from a large fraction of the solar surface, not just the polar regions, and it favored the dominance of this ion. And the dominance of this ion saying that there is the temperature in the corona somehow is capped at a certain temperature. I should say the temperature of all the particles that are streaming away from the sun seem to be capped at one given temperature. It doesn't vary, like it could go to 2 million, like, for example, iron 14 is at 2 million, but that's not what you observe in interplanetary space. You only see iron 14 when you have this explosion at the sun, and these hot particles are released. So this was the first, after collecting data over more than 15 years, we were able to establish the sources of the solar wind at the sun and the dominant electron temperature in the corona. So now we have to, or theorists, anybody who wants to do modeling and theoretical investigations, they have to try to figure out what process is keeping the temperature so fixed. Like, why doesn't it go widely up to 2 million, 3 million, 4 million, or go below? We still don't know. Now, I want to change to a slightly different aspect of the corona, and this is what we call the dynamic corona. It's produced by, it's really instigated or triggered by prominences, and they produce what we call coronal mass ejections. Now, this is a picture from 2012, and you can see the sun is very, very complex. You can see these prominences that are usually very close to the solar surface, but once in a while they kind of erupt. We catch them in the eclipse images almost like suspended, but all it is that they had started to move out of the corona, but they still remain like tethered to the solar surface. So what do these produce? Did I show this one? This is another composite. Okay, so I want to show you that how valuable the eclipse observations are, even when especially in the case of coronal mass ejections, which can have dire effects on this Earth's magnetic environment. So on the left is the eclipse image, which was taken at a given time on November 3rd, November 2013. And on the right is exactly the same time from the space-based coronagraph, so that you can see. So what we captured in white light is this huge, it's like a twisted rope, and it's surrounded by something that looks like a light bulb. And this is what we call coronal mass ejections. But the beauty of the space is that you have the time sequence, so you can see how things started and how they evolved. But you're missing this gap, and it's the eclipse image that's going to fill this gap. So let me run the movie. So I'd like you to focus just on this southern area to see how this thing is going to emerge. So there is a precursor to it over here. And then all of a sudden, this thing starts to happen, and I want to stop it here. So you can see that this exact time of the eclipse was present in, of course, you would expect this. But the amazing thing about the eclipse image is that here you wouldn't know that this bubble stayed connected to the sun, but here we see all the tethers that are holding this still at the sun, and they expand into interplanetary space, still being tied down to the sun. Now, okay, I'll skip this one because, okay, during solar maximum, you have more of these coronal mass ejections. They happen in all the sides of the sun, not just in ecliptic or polar regions, etc. This is the image from 2017, where we now having these filters which capture the different temperature plasmas. We found that this complex structure was due to a coronal mass ejection that was going through the corona during totality, and we know that it was carrying the hotter material in the corona. This one is the trace left from the ejection of this coronal mass ejection. Once it went through the corona, it kind of wreaked havoc all around it, and it changed the structures. It moved them apart and so on. And then slowly the sun comes back to being like quiet down and go back to its more stationary or stable state. So how are the prominences connected to these coronal mass ejections? Well, this is one of my favorite images we have from the 2008 eclipse, where this was this huge prominence sticking out of the sun, and we had these gorgeous iron images which showed that in the shroud of this prominence. So the prominence is at about 20,000 degrees, 50,000 degrees, and here you have a shroud of 2 million degrees, and it's always the case that these prominences are always enshrouded by the hottest material in the corona. And that's another big question in physics, like how can such a thing happen? This is a close-up of different prominences showing you how they're intricately connected. So here you see this pinkish emission kind of connected in a strange way to the overlying gas, because you see the prominences have such intricate the magnetic field associated with the prominences is not this type of laminar structures that you see in the corona, but really very complex and kind of deformed and so on. Okay, this is another example of all the kinds of what we call turbulence, or things that are kind of, well, for example, when you see clouds in the sky, or when you have storms, you have turbulent gases mixing with each other. The same thing happens in the corona. And the question is, how does this evolve into interplanetary space? So this was from 2020. It was caught by an amateur. We were clouded out where we were, but he wasn't. You can see this huge coronal mass ejection. And then now this is not taken at the same time, but there is one instrument on the Parker Solar Probe, which is the closest spacecraft that's orbiting the sun. And they see structures, they captured a structure like this, which is almost identical to what you see at the sun. Now, they're not at the same time, but it's the same type of feature. So it's clear that what's emerging from the sun stays, it expands, or it moves outwards, but it doesn't change its shape. It kind of preserves its shape as it's moving away. And this is another example of these little islets, what we call some kind of a like mushroom type features, plasma instabilities. And you can see that at 100 radii away from the sun, they're still there, and they were captured by the Parker Solar Probe. So these things don't just disperse in the medium, but they really keep their identity, and they just go out with the solar wind. Okay, so in 2021, the only place we could go to observe the eclipse, it was over Antarctica. We had to be on a vessel because there was one site on land, but it was prohibitively expensive to go there, and you couldn't carry this whole suite of instruments that I showed you. So our other option was to be on a vessel, so we ended up, we were funded both by NASA and NSF, so we had two vessels, hoping that if one was clouded out, the other wouldn't be. And so we had to develop certain, we had to use gimbals and stabilized platforms for our equipment to offset the motion of the ocean. And so this was a spectrometer here on the right, which was handled by Ronan, and here were the one pair of imagers which were on a much simpler gimbal. So this was in the one of the vessels I was on, and unfortunately, so as we were up, this is just a picture of so this is the day before the eclipse, and this is unfortunately the day of the eclipse. So it was solid gray. You could feel that the eclipse happened because everything darkened, but we could not see the sun. So this was heartbreaking. Another heartbreak. So one of my younger colleagues turned to, we had with us Lika Gohatakurta, who's she's the program manager of the funding eclipse observations at NASA. So he turned to her and he said, "Has anybody flown a kite, with a payload?" She said, "No." He said, "Well, is there?" She said, "But we do have a program for innovative technologies." So we decided, and this is Benedict who came up with this idea. So we thought, okay, we submitted a proposal to fly a kite during a total solar eclipse. Now, our first opportunity was this eclipse in this April to test this technology. So we literally had 8 months to try it. So to make a long story short, we found it wasn't the original attempt, but Bene found two amateur astronomers. He's from Germany. So Clemens is the one who actually built this kite. It's what you call a Cody box type kite. And this is the team who worked together on the payload. So, and there's also my colleague Adalbert Ding. So behind this nice poster is a spectrometer. So it consists of a ciliostat that kind of tracks the sun, and the light goes from the top here into the spectrometer. And here you have a detector and a grating and so on, and you get a spectrum. So the idea was, okay, we're going to hang this thing on this thing and see if it will get the spectrum. So I want to show you a fun, this is the video. This is the attempt to fly it. It was not easy. So I don't know if you can hear it. This is the sound of the wind. And this is us attempting to attach the payload. Yeah.
Quack, quack, quack.
We had to have some of us necking because the flies were yeah.
It's doing video.
Sorry, did I restart?
Okay. Bye-bye, Quack.
Yeah. Quack, quack, quack.
And this sound you hear is we had to have a parachute. I'm going to, there's a little parachute here, and the parachute releases automatically if it feels a sudden drop in gravity. Fortunately, it didn't release because we stayed there. So this was somewhat nerve-wracking, but it made it. So the highest we could fly was 600 meters because we were limited to the landscape because to the left of this picture was the ridge, and we couldn't really climb the ridge to stretch the tether, and we didn't have a winch. So this was our technology demonstration. And I didn't include a picture, but we actually did get spectrum. So it was pretty much of a, so this is a picture of the kite here and the payload. So for all these discoveries, we should thank them all. I hope you enjoyed the show, and thank you. So,
All right. Well, thank you very much. This is really wonderful. So a lot of really great imagery and a lot of really great, all those details down in that inner corona. It's remarkable what
yes.
when you really bring them out like that. So thank you. So we've got a number of questions here. If anyone else has any other questions, please make sure that you jot them into the Q&A window. We had a question very early on, and I know that you addressed this, but I'd like you to remind us again, just because it never hurts to hear this again. So very early on, we had a question: how is the million-degree temperature of the sun's corona determined? And so, if you could maybe refresh our memory of what that is here at the end.
Oh yes. So do you want me to go back with the slides, or I can go?
Or you can just answer.
Yes, I can answer by telling you that if you remember, I told you one of the first discoveries in the corona was the existence of this coronium. So in the spectrum, there were different colors that appeared, but this particular line, so with a color is associated a wavelength, and is you associate these colors with different elements, whether they're neutral or ionized. We don't know. They didn't know at the time. So this color was discovered. But for example, if you have a hydrogen lamp, it emits it's pink. If you have a helium lamp, you have different colors. There was nothing that was known in the lab that would emit at this wavelength. And it wasn't until 1941 that two people realized that the temperature of that this emission line came from iron-13. And iron-13 plus couldn't exist except if the temperature is at almost 2 million degrees. So that was really how we discovered the temperature. So in our observations, we choose different. So now we know it's not just iron-13 plus that exists in the corona, but a whole sequence of different ionization states of iron that give you a sequence of temperatures from 1 million to 2.5. So this is how we know the temperature of the corona, by measuring, observing these lines and seeing where they exist, where the emission exists in the corona. So what we found to be dominant is this iron-13 plus and the iron-10 plus at 1 million degrees. So it's almost like the corona likes to have the 1 million degree for everything that's streaming away from it, and the 2 million for everything that's bound to the sun.
Right.
Why is that the case? We don't know.
Yeah. So we had one person was really interested in the coronium, and and then they speculated about it being on Earth, but if it only is stable or is only present at, those high temperatures, we better hope that we don't have any found on Earth, I suspect, so.
Well, you do see them in interplanetary space. You see these ions, but that's not the temperature. I mean, they are the remnant of the temperature in the corona, but the solar wind has a temperature of about 100,000 degrees when it reaches the Earth's outer magnetic environment. We're shielded by the solar wind to some extent because of our magnetic fields. But if you go into space now, of course, these temperatures are, because the gas is so tenuous, it's like you put your hand in the oven, but you don't burn it. I mean, it's hot, but unless you touch the racks or something, you don't burn your hand.
Yeah.
And it's the same thing. Mm-hmm.
So that brings up an interesting question about the extent of the solar wind and how far out you can detect it and study it. One person asked about if either of the Voyager probes are able to gather info about the effects of the solar wind and how that and some of these other more distant missions can enhance this understanding of the solar wind.
Yes, so the Voyager, so after the discovery of the solar wind, there was this long scientific discussion as to where does the solar wind meet the interstellar medium? There has to be some kind of a transition. Where does this transition happen? So lots of theories were developed. Some said, at 50 AU. Some said, well, maybe 200. And at the end, when the Voyager spacecraft reached, there was a signature of the termination shock. It was around 80 to 90 solar astronomical units. Now, the thing is, we now know that because the corona changes so much, the distribution of the solar wind around the sun changes. And therefore, this boundary is not fixed in space. It has to vary. And it could be that it was when the wind was fast, it was further out. And then when the wind slowed down, it came further in. But the spacecraft is still moving. So it's a matter of it catching this termination shock at the right time. So it's not a fixed boundary, but now it's around 90 AU. And so it's another kind of demonstration that the solar wind expands in all directions away from the sun, and that its variability is detected everywhere.
Hey, kind of going back to the idea about the corona, and so we have these very high temperatures. I guess we'll stay with this for a moment. What is the current idea, the current thinking, the theory about why it's so hot, since the surface of the sun is cooler?
Mm-hmm. So there are several theories. I think one of the physical processes could all be there, except they work or impact the medium in slightly different ways. And so, for example, there's a process called magnetic reconnection, whereby if you bring magnetic fields very, very close to each other, the gas pushes them together, but they are in opposite directions. So what happens is, imagine you have like two field lines coming close to each other, but one is one is north-south, the other is south-north. And what happens is they reach a region which is so small that they diffuse into, the gas diffuses into each other. And these two segments kind of snap and one connects. It's like two X's. This part of the X connects with this one. So they reconnect and they split. Now, when this happens, you have a very large current. So you have two things happening with reconnection. You're changing the topology of the magnetic field in the corona, but you're also inserting a lot of energy locally. So if these processes occur very, very frequently, then you are injecting a lot of energy in the corona that might be heating the gas. That's one idea. The other idea is that you have waves. So unlike water waves or sound waves, because we have a magnetized medium, an ionized medium, and magnetized medium as well, There are waves that are produced that don't exist naturally on Earth, and those are called magneto-hydrodynamic waves from magnetic and sound waves. And these waves can also impart energy to the gas. So they are there, they develop from disturbances in the medium, and then they can kind of dampen. And when they dampen, they lose their energy to the gas, and the gas can get accelerated. So these are the two dominant theories at the moment.
And I think you just answered this question. This is I like the way that I didn't find this one until after I asked that one. But this kind of relates to that. Maybe gets a little bit more about how can a hotter temperature exist above a colder temperature, and why the corona is warmer, pressures of the material, why hotter away from the sun, and what the energy source is. And I believe you just answered that. It's magnetic energy. So that's
yes, exactly.
Great, thank you. So here's a good question. Let's see, where did it get to? I just lost it. Kind of about I think that we could infer what was going on with why you're using a kite, but one person said, well, what was the goal of doing the observations from a kite?
Okay, so the original goal from a technological point of view was the kites can fly up to 4,000 or 5,000 meters. So it's the height of Mauna Kea, for example, or above. So they can get above the clouds. If the clouds are, at that height. If they're higher, of course, you can't get to. And the kite is a fairly stable platform, because once you get to that height, the atmosphere the turbulence has almost disappeared. This is why you have the large telescopes on these high mountain tops. So now, of course, so the idea was, okay, let's test this technology, whether we can fly a kite with a payload of 16 kilograms in this case, and whether the payload can be stabilized to the point where it can observe the sun. And we chose a spectrometer. Well, we have two types of observations with either a spectrometer or the imagers, which I showed you. I didn't show you the results from the spectrometer, but the spectrometer tells us what kind of elements exist in the corona, whereas with the imagers, we select the iron 10, 11, whatever, and we image in that line. Although the weather was clear, but we really wanted to have a technology demonstration, in particular for 2024, to show that, sure enough, we can launch the kite with such a payload, we can stabilize it, and we can get data from the corona. So in case of, because if you're clouded out and you have a kite with you, then you can just strap your payload, attach it to the tether and fly your kite, and you haven't wasted or lost the whole opportunity. That was the idea.
Great.
So it's really just to overcome the clouds.
Yeah. Well, with all these amateur astronomers, they're all interested in, telescopes, and they're all interested in the devices that they use, imaging devices. And so we have a question here about your how narrow were your narrowband filters? Where did you get them? Were they specially manufactured for you? And I suppose the underlying question is, where can I get them? So.
Okay, so they have to be special ordered, and the specs have to be defined by us. So for a long time, we used filters that were manufactured by Andover Corporation in New Hampshire. And the bandpass of the filter is, if you prefer angstrom, it was 5 or half a nanometer wide. This year, we moved to another company called Aluxa, because one of the disadvantages of the Andover filters is that they had to be thermally controlled. So we always had a heater around the filter, and we had a system. They obviously needed power to keep them at a certain temperature. So the power requirement was much more demanding than with the current filters. The current filters do not require any heaters, so the total system ends up being a little bit lighter, and it's less energy demanding. And as I said, the beauty of the eclipses is that you can take advantage of the advancements in technology. So we also used a new set of cameras, which are called SWO cameras. So to get back to the question of the filters, so the filters, yes, they have to be specially manufactured, and they are not cheap. For example, for Andover filters, they were about $5,000 each, and the heater itself was another $3,000 or $4,000. So the whole each one is about $8,000. This year, the Aluxa filters were slightly cheaper if you ordered more than one, and the advantage was there was no power requirement to keep them thermally controlled. So you do have to special order them, and it's costly. Yes.
There are a few amateurs out there that they would definitely pay that to get these filters. So, okay, we're going to.
I must emphasize that if you want to observe in any specific line, remember you have to observe the continuum that's next to it. So you have to buy a pair of filters, so that you can subtract the two from each other.
We're going to go two more questions, and then we're going to apologize to everyone whose questions we don't get to. We're right at the top of the hour, but I want to get to two more. And so here's a good one. It has to do with the where the iron is within the sun. And so it was asked, does iron exist only in the solar corona?
No, it exists in the photosphere. There are lots of photospheric lines from neutral iron, for example. So from the sun, you get practically all the elements. It's just that it just so happens that iron is one of the more abundant elements, and it produces all these emission lines. So it's easy to observe. But you have nickel, you have argon, you have oxygen, carbon, magnesium, you name it. They all exist. But in the visible part of the spectrum, the iron is the most dominant emission line.
And a follow-up, and then I do have the one other question, but a follow-up to that. And so some people might ask, is the iron being created within the sun, or is the iron from a previous generation of stars and it was in the sun when it collapsed from the molecular cloud?
It's the latter. It's the iron is the composition of the sun was really from remnants from supernovae explosion, because the sun doesn't have the characteristics to produce iron itself. So it is embedded in the sun.
Okay, great. Okay, last question. And so here we have, do you have any comments on this last week's auroras caused by some major solar event, or anything related to what you've been doing, or just any comments at all about the display that we've had?
Yes. So as I mentioned, those are the coronal mass ejections. Okay, so remember that the sun is a magnetized medium, and the solar wind carries the magnetic fields with it as it goes into interplanetary space. The Earth is one of the planets, or most of them, but not all, have strong magnetic fields. So they do shield themselves from the impact of the solar wind when it approaches the Earth. But there are regions where you can have this magnetic reconnection I mentioned, where the particles from the solar wind can penetrate the high latitude, or they become lower as this impact is stronger. So what happens is, the solar wind by itself can produce, these aurorae, but if you have a coronal mass ejection, it's much more powerful. So if we, what we can say from the eclipse observations is that we have detected far more coronal mass ejections than just the spacecraft in interplanetary space, because we're much more sensitive to the very faint ones. So we know that and what we can also discover is how, what is the temperature of the gas that's dominating this coronal mass ejection. And our observations are the only ones to give this kind of information. So we can follow them from their beginning at the sun all the way as they expand into, well, to the visible, to our field, the edge of our field of view, but we can say something about their physical properties that no other instrument at the moment can tell. So our hope is to be able to characterize them so that when people try to run models and they have some boundary conditions observables from our eclipse observations, that they can either predict the occurrence of CMEs or how they will evolve.
All right. Well, thank you very much. This is fascinating. Great imagery, great information, and it's wonderful how you are able to talk about the different research that you're doing about this elusive part of the corona that we can only see every once in a while. So, and that's all for tonight, everyone. Thank you very much, Dr. Habbal, for joining us this evening, and thank you, everyone, for tuning in. You'll be able to find this webinar, along with many others, on the Night Sky Network website in the Outreach Resources section. Each webinar's page also features additional resources, activities, and links. This presentation will be on the Night Sky Network YouTube channel very shortly. Also join us for our next webinar on Tuesday, May 23rd, when Brian Day returns to update us on the current status of lunar missions. In addition, the Globe Eclipse team will join us for a webinar on Tuesday, May 16th, to show us how we can participate, contributing to NASA eclipse science through using the Globe Eclipse module in the Globe Observer app. So keep looking up, and we will see you next month. And Vivian, I think you want to remind everyone about the survey and about the little raffle that we're going to do. And so I'm going to let you wrap things up with just a final word on that.
Thank you again, Dr. Habbal. That I've been waiting for that talk since 2017. I really appreciate it. I want to let everybody know that we've got 5 of these awesome books called Totality, an Eclipse Guide in Rhyme and Science. It's a great book by Jeff Bennett. He's donated those. So if you take 2 minutes and tell us what you think of this series and what you want to hear about next, it doesn't take but a minute, and we can, 5 of you will be shipped one of these books. So yeah, Laurie, it's a great book. Thank you so much to all of you. We look forward to seeing you again at a future webinar. Thank you again, Dr. Habbal.
You're welcome. My pleasure.
All right. Well, this is wonderful. Thank you so much for joining.